All right, hello everyone. This is lessons 4 and 5, combined lesson in Unit 3 in complex numbers and exponents. Okay, folks. So this will be a fairly quick little lesson devoted to extending our knowledge of rational exponents. In one of our previous lessons, we looked at the nature of the expression say something like 2 to the exponent of 1/2. And we asked ourselves, well, what does 2 to the 1/2 power look like and what does it represent? And ultimately, we discovered that that equals the square root of 2. And that has to do with the fact that um, for any value of a, we have a to the 1/2 times a to the 1/2 uh, will equal a to the first, which is equal to a. Now, two of the same thing multiplied together to get a, that's also the definition of square root. So this leads us to believe that a to the 1/2 is equal to the square root of a. And that's just the big idea from the previous lesson. The same holds true with cube roots. And in terms of cube roots, a to the 1/3 equals the cube root of a because you need 3 copies of the 1/3 in order to get a whole a, if you think about it that way. Um, but that leads us to a more general rule, and that is a to the 1 over n power is equal to the nth root of a. And we know that for whatever function that we have, like if we have, say, a to the 1/7, then we're going to need 7 copies of a to the 1/7 in order to get to a whole a again. And so because we need 7 copies, that's equivalent to the 7th root. So that becomes the general formula. However, they all have one thing in common, and that is that the numerator of that fraction is a 1. Well, can we extend that to fractions that are not a 1? Like, what if I wanted to find, say, for example, a to the 3/7 power? Could I do that? What would that equal? And that's what this lesson's all about. Okay, and so our goal here is just really interpreting exponents in all their different forms. So are they fractions? Are they negative fractions? We're going to stop short of irrational numbers, though. That is kind of a different discussion, like 2 to the pi power. We're not going to really um, evaluate that here, but certainly anything that can be written as a fraction, what we call a rational number. Okay, so let's start with some basics, right? Again, remembering from the previous unit, and again, we already covered this on a uh, little introduction here. So what is 7 to the 1/2? Remember, anything to the 1/2 power is equivalent to a square root. Um, so, one thing that you might wonder as we do this is why would we need to know like how to write a number as an exponent, and then why would we have the same value written in a radical form? Well, the easiest way to think about it is one flavor of number, could be useful in one way. One flavor of number might be useful in a different way. And, this also serves to uh, allow to compare the values of numbers written in different forms. So, like, for example, knowing that these two are equal, you know, let's say you wanted to compare, say, 7 to the 1/2 power to, I don't know, the square root of 10 or some other square root, and say, okay, well, this is equal to root 7, so root 7 is smaller than root 10, something along those lines. Having a way to convert back and forth, at its core, um, gives us more flexibility in how we write the numbers and gives us more flexibility in determining how numbers are scaled in relation to one another. Okay, so let's fill out the rest of this. Now, what about 7 to the negative 1/2? Remember, negative exponents are not negative answers. They represent reciprocals or repeated division. So instead of having root 7, it's 1 over root 7. That becomes important in this lesson as well. 7 to 1/3 power. Well, okay, so that's going to be the cube root of 7 from what we did before. And so the negative 1/3 power is 1 over the cube root of 7, just like that. Okay, so let's take this knowledge one step further. Uh, what happens if I take one of these quantities, say, 5 to the 1/3 power, and I square it? Well, what's going to happen? Okay, so 5 to the 1/3 power squared. When I have two powers attached to the same base, they multiply. What's 1/3 times 2? It's 2/3. So the first expression is equal to 5 to the 2/3 power. 1/3 times 2. What if I took 5 squared to the 1/3 power? Notice the same values, but just exchanged. So is that going to produce the same value? And this is because multiplication is, now here's a special word that you might remember, commutative. Not sure if they teach that in elementary and middle school anymore. Multiplication is commutative, and what that means is that the multiplication can happen in any order. Is that, A times B is the same as B times A. Because of that, um, these two come up with the same value. So knowing this, could we write this expression in a radical form? Well, sure. Well, let's take a look at what we have. 5 to the 1/3 power, right? 5 to the 1/3 power, well, we know that that is the cube root of 5. But then that has been squared. But what if the exponent's on the outside? You could also do, looks like 5 squared, but then the 1/3 power means it's going to have a cube root affected to it. Now, 5 squared, in this particular case, 5 squared is a number that we know, and you could also say that this is the cube root of 25. Hey, now we get an idea. This is another, reason, as I was saying before, how it allows us to compare values. So look at 5 to the 2/3 power. Before doing this, would you have any indication as to what its value is? Well, let's see. 5 to the first is 5, so it's got to be less than 5. But now look at this. We write it as a radical, and all of a sudden we see that it's the cube root of 25, which is, the cube root of 27 is 3, so this is a little bit less than 3. That is powerful, and one of the reasons why, writing numbers in different forms is super helpful. Allows us to kind of understand more about the number. So, yeah, I know I'm kind of, hitting on that multiple times, but that is a very, important thing to realize, having multiple ways to write these expressions. Okay, what about 5 to the 4/3? So again, let's write it out. We can do it any one of these ways, right? So I could do the cube root, um, say 5 to the 4th, and I know this because 4 to the thirds is equal to, say, 1/3 times 4. So I could do an exponent of 1/3, there's my cube root, and 5 to the 4th. Now this is a little bit harder to do in your head. It's the cube root of 625. Another way to write it is by writing it with the parentheses, and to do the cube root of 5 squared. Okay, all three of these are correct and are accepted notations, depending on how much you want to evaluate and in what order the operations are considered. Um, but because we spent a lot of time talking about notation, maybe you wonder, is one better than another? Is there one that's a notation that's considered standard? The one that's considered, the most used by mathematicians is the first one here. Um, so this first one is kind of like standard for exact value. So that tends to be used when we need something written as an exact value. Now, sometimes mathematicians will also write it in terms of a exponent as well. So um, generally, as to which is preferred versus radical and exponent, um, I don't have any clear answer to you as to which is expected that way. But when written in a radical form, this first way down here sees a little bit more use. However, this third one here tends to get used more when safe to evaluate. Now, this particular expression is not because we don't know the cube root of 5. Um, but with this one, see, the idea is this one is sometimes better done in your head when the numbers work out. And that's because applying the cube root first makes the number get smaller, then get bigger. Versus here, the number gets bigger, followed by smaller. So this can present some problems. And I just realized here, this is not a 2. This is a 4. My bad. Okay. That should be a 4. So when the number does not work out like this, where you have, like, you can't find the cube root of 5, generally you're going to write it in this first form. Um, Again, they're all correct and I'll gladly accept any of them, but this way is really more useful when you are able to complete that calculation by hand. A good example of that, let's see, I think there might be one on the, um, maybe not on this slide here, but just kind of an example I'm thinking here. If I wanted to find 8 to the 2/3 power, okay? If I wanted to write that as a radical, it would be the cube root of 8 squared. And that's useful here because we know the cube root of 8. That's 2. So that's equal to 4. So that form is useful when we can just quickly do the calculation. Okay, here's another example. Here's another good one here. Um, the fourth root of 9 squared. What is that? So the fourth root of 81? Might you know what the fourth root of 81 is? Hmm, maybe, maybe not. Maybe let's try writing it as an exponent and see what happens. What would this be as an exponent? It would be 9, and when you're turning this into an exponent, the radical piece, the radical number, is the denominator. So it's going to be 2 over 4. Now, 2 over 4 simplifies, doesn't it? Does that simplify to 1/2? Guess what? It's a fraction. It's an exponent. Doesn't matter. It can simplify. And it becomes 9 to the 1/2 power, which we already know is the square root of 9, which must be 3. And the fourth root of 81, well, 3 times 3 times 3 times 3. Yep, that is certainly equal to 81. So it works. Um, so here's a clever little trick. Exponents that are fractions, those fractions can be simplified to lowest terms. Okay. So there's lots of different ways. Express the number 16 in as many different ways using exponents or roots. Okay. There's lots of ways you can do that, right? Um, we'll start off with the basic. How about just 16 to the first? Maybe 4 squared. Is it a power of 3? No. Hey, it's a power of 2. It's 2 to the fourth. Well, let's see what else. It is. Oh, now 2, right? Now this 2, we can mess with this, right? And say that we can change 2 to maybe a root. We know that 2 is the cube root of 8. So we could write this as the cube root of 8 to the fourth power, which makes it equal to 8 to the 4 thirds. All right, what else can you do? Oh, lots of ways, right? Um, 16, 16, so 8 to 4, what else? 8 to the 4 thirds. Could you do maybe some power of, so let's see, 2, 4, cube root of 64 squared. 64 to the 2 thirds power, 60. Knowing that the cube root of 64 is 4. You could also do cases like 16 squared is 256. So the square root of 256, or 256 to the 1 half, that works. So there's lots and lots and lots of different ways. These numbers can get written in fractions almost as many ways as you could ever possibly want. Okay. Yeah, that works. Okay. All right. What is 2 5 thirds raised to the third power? Ooh, 2 to the 5 thirds to the third power. What's going to happen here? What's 5 thirds times 3? Well, the threes are just going to cancel out. Division by 3 multiplied by 3. And you're just going to be left with 2 to the fifth, or 32. How would that look in radical notation? Well, it looks like I would have, 2 to the fifth. So I would have 2 cube root of 2. And so I would do cube root of 2, and I could raise that to the fifth power. Or I could put the 5 on the outside. Doesn't matter. I could do cube root of 32. Or I could do um, the cube root of 2 to the fifth. Either way works. Any of those are fine. What two whole number powers of 2 does 2 and 5 thirds come in between? Well, 5 thirds is like 1 and 2 thirds, right? So it's between 2 to the first and 2 to the second. So we know it's between 2 and 4. But can we go even one step farther? We know it's the cube root of 32. And if we know it's the cube root of 32, it's just a little bit more than 3, right? And it's going to be closer to 3 than 4, right? Because it's just a little bit past the cube root of 3. So it's going to be a bit more than 3, the low end of 3. So, we can tell lots of things about these numbers. Okay, so that concludes the lesson 4 part. Um, all right, so a little bit of a summary here, just kind of going through and determining like how we can write back and forth between a radical and a rational exponent. Okay, so really nothing more fancy than the rules we have. Really not a lot of exceptions. Okay, here's the lesson 5 piece. Here we're going to take a look at what happens when we have a negative exponent. Um, Really, it's kind of more the same because we already dealt with some negative exponents before, but let's see what it looks like for these problems. Okay, so see, oh, there we go. Let's bring that back a bit. What's 9 squared? 81. No big deal there. What's 9 to the negative 2? Remember, reciprocal. 1 over 81. 9 to the 1 half? Square root of 9, or 3. 9 to the negative 1 half? 1 over root 9. 1 over 3. Interesting. So 9 to the negative 1 half is 1 over 3. Okay, so in each case, best way that I can think about this is kind of at first ignore the fact that it's negative and find like 9 to the 1 half power. But then the negative comes in and it just makes your answer into a reciprocal. Okay, so now let's look at a little game that I guess we could play. Which one of these does not belong? For each set of 3 numbers, cross out the expression that is not equal to the other two. Okay. 8 to the 4/5, 4th root of 8 to the 5th, 5th root of 8 to the 4. Which one's different? Well, clearly these are different, and we have to figure out which one matches 4/5. Remember, 5. Oh, that's the radical. That must be the index. So therefore that works. It matches. Okay, that one's out. So that would be an exponent of 5 over 4. Okay, same idea down here. 8 to the negative 4/5, 1 over 5th root of 8 to the 4, negative 1 over 5th root 8 to the 4. Oh, they both have the 5 in the right spot this time. Which one's the odd one out? Ooh, the negative. Remember, negative exponents. Any number, so a positive number raised to any exponent will be positive, always. And that has to do with, the domain and range of the exponential function. So positive number to any exponent will always give you a positive number. And that's any exponent, positive, negative, fraction, you name it. That one's out. Okay, square root of 4 to the 3rd. So that's going to equal, this is like a 2, so we'll have 3 over 2. That matches, that matches, that one's out. Okay, and 1 over root 4 to the 3rd. As we said before, your answer will never be negative for that. So we'll cross that one out. So it becomes 4 to the negative 3/2 power. So again, see the connection between the negative and the reciprocal. Okay. Match expressions in the group according to whether they are equal. Ooh, fun. This ought to be interesting. So I suppose what we'll do is we will have, now we could have multiple groups. This doesn't say we're going to get 2 groups. We could potentially have more groups. So let's see what we have. Okay, square root of 3 to the 4th power. Well, let's see. That's going to be 3 to the 4 over 2, which is 3 squared, which is 9. So that must be equal to 9. And you can prove it by taking the 4 and moving it to the inside. You get 3 to the 4th, which is 81, and the square root of 81, we should know that. That's 9. Okay. Square root of 3 squared? Well, 9. Square root of 9, 3. Okay. So that matches nothing yet. Okay. 1/2 to the 4th. Oh, that matches A. Okay. So I'm going to put an A. I'm going to put an A. I'm going to put a B here. Okay. Root 3 squared times root 3 squared. Well, that's the same thing as saying root 3 to the 4th. So that's also going to match A. And aren't you just going to have 3 times 3, which is 9? Yeah, so this is 3 times 3. Okay, let's try a few other ones. 3 squared to the 1/2. Well, that's 9 to the 1/2. That's the square root of 9. This must be equal to 3. So that belongs in a group B. 3 squared? Well, that's 9. That's part of group A. 3 to the 4 over 2. 4 over 2 is 2. That's also A. And 1/2 squared. 2 exponents on the same base. We multiply those. That's in group B. So we have 5 members of group A and um, 3 members of group B. So it's all about figuring out whether or not they have like exponents, and that's really what it boils down to. Okay, so lots of little expressions that we can do here, right? So again, just really a lot of practice on, um, being able to um, convert back and forth. So here, if it's written in one form, write it in a different form. That's really what we're trying to go with here. Okay, let's try a few out. So like the first one, 5 to the 3/2 power. So can we write it as a radical? Well, let's see. Square root. Okay, so the 2 says it's a square root. So square root of 5 to the 3rd. That works. Um, you could also do root 5 to the 3rd. Either way. But at this point, I'm going to kind of take that as an understanding. So generally, I'll pick one of these methods to write it. At this point, rather than just always writing out all 3 of them, I wouldn't expect you to write all 3 of them out. So I'll just pick whichever one, seems at the time to make the most sense. And you'll get a chance to see as to, why I chose the one that I did. Okay. Um, so 1 over root 2 to the 3rd. So again, just focus on the radical part. Let's turn that into a exponent, right? It becomes 2 to the 3/2. But the fact that it's 1 over makes it negative. So 2 to the negative 3/2 power. All right. 6 to the 1/4 times 6 to the 1/2. Well, let's see. Separate bases. Let's add the exponents. This is equal to 6 to the 3/4, fourth root of 6 to the 3rd. I'll generally default to this way of writing it, even though you could put the 3 on the outside. Okay, what about this one? Okay, it's the radicals, so let's take all the radicals out. Let's see. You have a couple ways that you can handle this. But first, maybe let's just turn them both into exponent forms, right? So 1 over root 10. Oops, made a, there we go. So that would be 10 to the negative 1 half times 10 to the 3 halves. So same bases, let's add the exponents. Negative 1 half plus 3 halves. What is that? Almost 3, that is 2 halves. 1, 10. That's expression. It's a messy looking expression, but it's equal to 10. All right. What about 7/3, 5/3? Okay. Again, we have the idea that these parts, again, you have a multiply these, and since you have a multiply and a divide, they cancel out, and you get 7 to the negative 5. 1 over 7 to the 5th. Either way works. And last one, 5, 5th root of 3 to the 1/3. Careful with this one. It becomes 3 to the 1/5 to the 1/3. It's very easy to look at that and think, oh, 3 to the 5/3. Not quite. This is a tricky one. It's 3 to the 1 over 15. Do be careful with that one. So always take it one step at a time. Um, and remember that like radicals always get written as a fraction of an exponent, always. All right. So there's some simple recognition for you on many of those factors. Okay. So one last time here, negative exponents are the reciprocals of terms with positive exponents. Same magnitude, same number, same value, but a reciprocal. Okay, and there you have it. So, all right, I hope that made a lot of sense, and hopefully not too long of a video here, and you can use this as you need to. It's been a pleasure, and next time that we chat, we'll be talking about solving equations using radicals and exponents. Have yourself a lovely time. Take care.